All right, well, let's go ahead and get started. Thanks for coming so early. I appreciate it. Looks like I'm talking in a very focused way to one of our major audience members. I really appreciate you coming. So today we're going to hear from Norm Loeb. And Norm is indeed a research scientist from the Langley Research Center in Hampton, Virginia. And his study is all about clouds and how much energy from the sun makes it through, not reflected back by the clouds, but to the Earth, and that's part of our Earth energy budget, and that's what makes all the difference in the world. Satellite observations, ocean data revealed marked increase in Earth's heating rate. All right, Norm, take it away.
Hello, my name is Norman Loeb. I'm the principal investigator of CERES, the Clouds in the Earth's Radiant Energy System, and I work at the NASA Langley Research Center. Next slide. We've heard about global mean surface temperature. We have a record that goes back to 1800s, and it's a really important variable, climate variable. But it's not necessarily the most fundamental. Perhaps more fundamental is the Earth's energy budget. What fuels the climate system is how much of the sun's energy is absorbed by Earth, so the absorbed solar radiation. The Earth actually sheds heat by emitting outgoing long-wave radiation to space. Our satellites are measuring these quantities. We have a source and thesis that measure how much of the sun's energy arrives at the Earth. CERES measures the reflected solar radiation as well as the outgoing long-wave radiation to give us a complete picture of the top of atmosphere energy budget. So when there's no external forcing acting on the climate system, these quantities are equal, and so the net is zero, and the climate system is in equilibrium. So in this case, when you average over a long enough period of time, the temperature remains constant. Next slide. We are forcing the climate system, however. We're adding greenhouse gases like CO2 and methane. As a result, these greenhouse gases trap thermal radiation from the surface and reduce the outgoing long-wave radiation. As a result, now the absorbed solar radiation is larger than the outgoing long-wave radiation, so that the net then is greater than zero. And this quantity, this net, is also referred to as Earth's energy imbalance. So where does this excess energy entering the system go? About 90% is stored in the ocean as heat. The remainder warms the atmosphere and land, and melts snow and ice. And the next slide I'll quantify those values. So in this case, because we're forcing the system and we have more heat coming in than going out, the surface temperature will increase when you average over a long enough period of time. But when you look at up to a few decades, the situation is more complex. Natural fluctuations, for example, from El Nino and La Nina events, cause changes in ocean currents and atmospheric wind patterns that can cause variations in surface temperature in such a way that it could offset or augment the increase in surface temperature associated with global warming. And we saw that an example of that was the so-called global warming hiatus at the beginning of this century, where the rate of increase in global mean surface temperature was less than it had been in the 2 decades prior. And that was essentially because of the period was dominated primarily by La Nina events, which tends to bring cooler waters to the surface and reducing the air temperature just above that. Next slide. So this excess energy, 90% is in the ocean. It's only 2% that's heating the atmosphere. So the warming that we've seen, the surface temperature warming of about 1.2 degrees, it's really a small part of this excess energy that's responsible for that. 5% warms the land, and 3% is used to melt snow and ice in primarily polar regions, but also glaciers elsewhere. So this heat then in the ocean is really important because if the system were to restore equilibrium, it would have to increase the surface temperature to shed more heat in outgoing long-wave radiation. So given that there's energy stored in the ocean, there's about 0.5 degrees of warming that's already in the pipeline that we're already committed to, regardless of whether we stopped forcing or not. So in addition to the 1.2 degrees, there's already another 0.5 degree or so that will happen because of the current imbalance, energy imbalance that we have. So the satellites really give us a complete picture of these quantities. I mentioned the source and TESIS, which measure how much of the sun's energy arrives at Earth. Ceres measures the reflected solar and the outgoing long-wave radiation. And we really get the spatial distribution of these quantities in very good detail. So these are month-to-month plots. You can see the dates on the upper left. And you can see what's causing the fluctuations in the system, primarily clouds, which are really important and something we're studying hard in climate research. Next slide. The other way of looking at the energy system is looking at the energy in the ocean. So I mentioned most of this excess energy is in storage, in ocean storage. And so we have a really nice network called the Argo Ocean Profiling Network that measures temperature and salinity down to about 2,000 meters. And from that you can measure the ocean heat content. So you can actually see how much storage is taking place and measure it directly. And this map shows the distribution of ocean floats and the countries that have contributed. So this is from February 2021. The number of floats reached critical mass around 2005. Next slide. So given that we're observing Earth's energy budget at the top of atmosphere and most of the excess energy ends up in the ocean, then the measurements of the ocean heat storage and the top of atmosphere energy budget really should track one another. So this is showing in red the Ceres net radiation, and in blue the planetary heat uptake, which uses the ocean in situ, the Argo measurements, together with measurements of heating over land and the cryosphere, the snow and ice melt, as well as the atmosphere. So putting all of the components together. And they track each other very well. And one of the things that really alarmed us was the trend that you see. These dash lines are really very consistent. And more alarmingly, they're showing that the Earth's energy imbalance doubled between mid-2005 and mid-2019. And so that was a pretty scary result given how important this quantity is. Next slide. This shows the cumulative amount of energy, the heat content from Ceres going from 2000 onwards. The monthly mean is shown in yellow, and so you see fluctuations. It's basically the annual cycle, which is primarily Earth-Sun distance related. The red line is the 12-month running average, and what you're seeing is a steady increase of the uptake of energy in the climate system. And you can contrast that with the global mean surface temperature, which has a lot more fluctuations in it, and that's really just a point at the atmosphere-ocean or surface interface, whereas this quantity is the integral of energy exchange between the Earth-atmosphere system and the and space. So it's really a more basic measurement of energy exchange than surface temperature is. So to put this into context, this increase in energy that's being taken up, if we look at the cumulative planetary heating that's taken place from 2000 to 2020, it's 226 zettajoules. The global primary energy consumption, by comparison, over that same period is 10.4. So the planetary heating is a factor of 22 larger than the global primary energy consumption. So it's a really lot of energy that is being added. So what are the impacts? What are the symptoms of a positive energy imbalance? There are many. A rise in surface temperature, which I've already discussed. It also causes an increase in atmospheric moisture, global mean sea level, shifts in atmospheric circulation patterns, which will lead to more extreme weather like flooding and droughts, and increases in ocean heat content, which would cause ocean acidification, which also has impacts on fish and other marine biodiversity, and a decrease in land and sea ice and snow cover and glaciers as well. So there are many impacts that are important to us caused by this energy imbalance. So next slide. So what causes this? What are the possible reasons? Well, we mentioned the forcings. We mentioned the greenhouse gases. You could have forcing from changes in solar radiation, but that's not the case in this. Since we're measuring how much sun's energy arrives at the Earth, we're just not seeing a big impact from that. You can also change the aerosol amounts, more absorption, but we're not seeing that either as a big player. There's also feedbacks. If you force the system and it warms, then you can have changes in clouds, water vapor, as well as the surface albedo. And those are playing a much more important role. Again, at timescales of a few decades, both of the internal fluctuations in the climate system, as well as the forcings, are really important. Next slide. So what we did is we used other instruments that fly with Ceres to try and get a better handle on what's driving the trends that we're seeing in the net radiation that I showed earlier. And so the bottom left plot here shows the contributions to the trends from clouds, water vapor, trace gases, surface albedo changes, mainly snow and sea ice, aerosols, and temperature. So the temperature contribution is negative here because we're warming the atmosphere, and so it emits more, so that's a loss of energy, so that's a negative contribution, it's a negative trend, it's a cooling effect. These others are in red, which are heating the planet, so the water vapor, if you heat the air, it can hold more water vapor, and it's a greenhouse gas, so it causes further increases in temperature. So what we're finding is the combined changes in clouds, sea ice, water vapor, trace gases, they're all positive trends, and they all exceed the negative trend that we're seeing from increases in surface temperature, giving you this overall positive trend that we're seeing. The other thing we've noticed is the cloud changes in particular are very closely tied to warming. This is the top right of this slide shows the trends in sea surface temperature that are showing a lot of warming in the eastern Pacific. The low clouds on the left in that region have decreased as a result, and you're getting a lot more radiation into the climate system. So these are probably tied to things like the internal fluctuations in the climate system. So in closing, we have a relatively short record of the satellite measurements from Ceres. And so we're finding a pretty alarming result. This doubling of Earth's energy imbalance is pretty alarming. And I think the cause is both climate forcing, as well as internal variability. And my hope is that this turns around, at least the internal variability portion turns around in the next coming decade, because as I mentioned, the implications of having positive energy imbalance, adding more and more heat, are pretty important. So thank you very much.
All right. Any questions? You know, the distribution of clouds are really important. You know, on the night side, we got more cloud concentration. That holds the heat. And on the day side, we have fewer clouds, and that means the water and the land have got to absorb it. So it's a double whammy. All right. And of course, Venus has got nothing but clouds. Mars only has a few clouds. All right. Any other questions? Thanks much.